Hello, everybody. I'm Jeff Miller. I'm a senior software developer and the lead developer for Sharding. And this is Harry Tong. He's a senior sales engineer. I'm going to be talking about our architecture and new features in the area of scalability. And then Harry's going to tell you about some use cases. As businesses grow larger, applications grow larger and handle more and more users and larger volumes of data, scale really does matter more and more. And InterSystems Iris Data Platform gives you a wide range of mix and match capabilities to scale up vertically and out horizontally, to scale users as well as data, to scale your business applications through SQL, as well as scaling using data scientists' analytic tools. We'll start by talking about vertical scalability, which has been around longer both in the industry and with InterSystems, and InterSystems has from day one excelled in this area. Vertical scalability, as the picture implies, is a relatively simple matter of throwing bigger and bigger machines as your problem gets bigger and bigger. So expand the capability of individual server by adding CPU, adding memory, I/O, networking capability, and it has an advantage of architectural simplicity. If you're used to thinking of one application on one machine, well, you can continue thinking that way, although there is some added software complexity to take advantage of features like multiple cores. If you know in advance pretty accurately what your data volume and performance requirements are going to be, then it's possible to tune the system with fairly fine-grained granularity to what your needs are. The flip side of that is, if you misestimate, you're going to end up investing in extra capacity that you can't use, or if you underestimate, you're going to have a system that's not big enough for your needs and you can't easily grow it. You have to go back to square one and replace it with a larger machine. And you have nonlinear price performance, so for each extra bit of performance, you're going to be paying more and more. Eventually, you hit hard limits to how high you can scale one machine. With each generation of machines, that limit gets pushed farther and farther up, but at any given time, the limit is there. Still, as I say, this is something that InterSystems has excelled at for a long time, and one of the recently added capabilities that particularly leverages vertical scaling in the SQL arena is parallel query execution, which allows you to take advantage of multiple cores by using a separate job to execute a query on each individual core. So transparently to the application, just by using the %parallel hint within your query, as in this example, the SQL compiler will figure out which table to use as the driving table of the query. It will automatically partition that table and assign a different partition of it to each job to run a query against that partition, and then there's a combining query that pulls the data together. So, yes?
What versions is this available? Is this now?
This has been available, is it 2015.1, Tom?
Yeah, it got pretty good around 16.1.
Yeah, so this has been available a couple of years now, and it's enhanced with each new release. It will be becoming completely transparent, but up through now, you still need to use the %parallel hint. And that's just a hint. The optimizer will figure out whether it can actually apply parallel. Now, horizontal scalability means scaling out using multiple machines rather than one bigger machine, so that you spread your data, your processing, your problem solving across multiple machines as your amount of data and your performance needs grow. This has much better price performance ratio than vertical scaling. If the software is designed well, you can get pretty close to linear price performance, and you have the option of using commodity hardware or using the cloud. So rather than having to have one super powerful machine that does it all, you can use whatever suits your needs best and just multiply by the number of machines you need to solve your problem. It allows elastic scaling, meaning, and there's degrees of how elastic is elastic, but in general, elastic means as your problem grows, you can throw more hardware at it. As your problem shrinks, you can redeploy some of that hardware for other needs. It's not all tied up in a permanent solution. It does add software complexity. It's harder to design applications that solve the same problem across multiple machines, although one of the challenges and one of the value-added pieces of a data platform is making this as transparent for you as possible so that your application can behave as if it was just a traditional single machine application, and behind the scenes have multiple machines carry the workload. There is more of an emphasis on networking. When everything else is tuned to perfection, the network is more likely to become the bottleneck since data needs to move around. So one of the challenges both at the application and at the platform design level is to try to minimize data movement. As I said, we can horizontally scale both users and data, so let's look at scaling users first, because that's something InterSystems has been doing longer. So to scale users, in front of what you would think of as your monolithic data server, you can deploy a set of machines, which we call application servers, and have a subset of your users or a subset of instances of user applications on each of those. This allows both parallelism in terms of having some user jobs executing on one machine at the same time others are executing in parallel on other. And it also allows scaling of cache, because while each user application is seeing the same amount of cache that it would have seen on an equivalently sized single machine, it's contending against fewer other users of the same cache. If you have one app server for every 3 users, say, instead of one app server for 30 users, then it's much more likely that the cache pages you need remain in cache. There's less cache thrashing and better performance. So in general, 2 particular levels of better performance are going to be the parallelism and the less cache contention. InterSystems specific solution for this, which has been around for quite a while and getting more and more robust and powerful with each release, is ECP, Enterprise Cache Protocol, which lets the application servers see the data by a shared cache server, so that all the application logic, including, say, your SQL processing, happens on the application server, and it's only at the level of serving up data pages that the application needs to go to the data server. Now, horizontally scaling data is a newer capability for InterSystems. In fact, as was mentioned in the keynotes this morning, this is something brand new with InterSystems Iris data platform. And so today is the first day we're talking about this to anyone outside the company. And this is sort of a little bit the inverse of scaling users, in that instead of putting multiple application servers in front of the data server between the users, and the data servers, we put multiple data servers behind what you might think of as your primary data server and partition the data across them. So the particular set of capabilities that provide this in InterSystems Iris is what we call SQL Sharding. And we didn't invent the word sharding. It's been used for a few years now in the industry to describe various approaches to partitioning data across multiple machines. But in most cases, as got mentioned in some of the questions this morning, people think of it as kind of a big serving up distributed data pages across multiple machines and using MapReduce or something like that, using kind of hard to learn, or at least for traditional business application programmers, hard to learn techniques to mine that data. With InterSystems Sharding, this fully supports SQL in a nearly totally transparent manner. It lets you use the same sorts of decision support and analytic applications against sharded data as you would use against conventional SQL data. This also scales cache, but in a different way than we scale cache with application servers. Rather than saying that each application sees the same size cache but with less contention, we're adding up the caches of all the data servers to provide a total cache size that scales with the size of your data. I'm sorry, I keep bumping the microphone. And that means for really large tables, you increase the chance that the entire table, or as much of it as possible, will fit in cache at one time, which greatly reduces your cache paging. So again, as with application servers, you're getting some speed up by the parallel execution of queries on each shard server, and you're getting some speed up by the fact that you've got a larger overall cache, reducing paging. Now, as I said, we allow mix and matching and combining of techniques, so you can have application servers in the front, you can have shard servers in the back. Also, you can combine vertical scaling approaches with horizontal scaling approaches. I said before that horizontal scaling allows you to use commodity hardware or use the cloud, but our sharding does not require that. You can use any kind of machine you want for each of your shards, including the same really beefed up heavy metal that you might use in a single vertical scale solution. You can combine parallel query, as we described before, with sharded queries. I should say that parallel query and sharded queries are conceptually very similar in that they are both splitting up the data into partitions that are queried separately and then combining the results. But the big difference is that with sharding, you're actually running each of those queries against a partition on a separate machine, which has a complete microcosm of the table. So a sharded table is split into pieces, each of which looks like a full table, including all of its indexes. This is a big advantage compared to earlier approaches that some of our customers have used, trying to partition tables with ECP alone, where they could partition their data extent and use union all style queries against it, but their indexes, because they're inverted, would have to be partitioned on a different set of keys. They were not partitioned along with the data, so you'd have to end up fitting most of your index pages in cache, so you'd get the same kind of cache problems that you would got in a conventional vertical scaling solution. Sharding eliminates that problem, and that's a big piece of its power. So let's dive into sharding in a little more detail. The basic roles in sharding, the basic instance roles, are shard master, which you have one of, and then shard servers, which you have any number of. So the shard master is what looks like the data server to your applications. It's what the applications connect to, or if they're running on app servers, the app servers connect to. And it's where the metadata resides, and it's where any non-sharded tables reside, because you don't have to shard all your tables, and you can transparently interoperate between sharded data and non-sharded data, which gives you a range of schema planning capabilities. The shard servers store the partitions of sharded tables, and any non-sharded tables, sharding leverages ECP by mapping the globals of the non-sharded tables to each of the shards so that they're visible from the shards so that you can join sharded tables to non-sharded tables without needing to replicate the non-sharded tables as other products tend to need to do. So, and this is one of a number of ways in which sharding under the covers leverages ECP. So sharding, although it's conceptually and in terms of its implementation a new thing with InterSystems, it very much leverages existing capabilities, makes ECP stronger than it was before, and makes our version of sharding much more powerful and flexible than competitors' implementations that don't have the kind of powerful, flexible distributed cache server that we have available in ECP. Now, as I think Simon mentioned in the keynote this morning, with sharding, we actually push the query to the data, which is another way in which it just is different from distributed approaches that we used in the past just involving ECP. So when an application issues a SQL query to the shard master, and the application, again, transparently talks to the shard master as if it was talking to any data server, doesn't have to be aware it's sharded. The sharding code running on the shard master looks at the query, says, okay, there's at least one sharded table here, so I'm going to shard this query. That means decompose it into a version that it sends to the shards to execute against the partition data there, and then a combining query. So it sends the shard master sends the query to each of the shards send the result of the query executed against that partition of data, and the shard master combines and aggregates and sends the final result back to the application. Now, I said you can combine scaling users with scaling data, so this is done using ECP application servers, but in the context of sharding, it's a more specialized role, which we call shard master application servers. When they're accessing non-sharded tables or accessing metadata, they're behaving just like a conventional ECP application server in that they're using ECP as a cache page server to get a data stored actually on the shard master data server. But when they're accessing sharded tables, they connect directly to the shards. The same sharding logic runs locally on them as would have run on the shard master data server if you didn't have the application servers. So your sharded queries run every bit as efficiently as if they were running directly on the shard master data server, except that you get all the benefits of scaling users across multiple app servers. I guess I should have gone with a lapel mic, but okay, that'll be an improvement for tomorrow's session. Or I'll put it on this side because I gesture with my left hand. Anyhow. Another specialized role is query shards. Now, query shards are essentially application servers of data shards. So without them, we just talked about having shard servers. For each shard, we now say we can have a shard data server and then one or more query shards that are app servers of it in the ECP sense. We decided to call them query shards rather than shard application servers because it would be confusing since your application code is not running on them. They're internal and transparent to your application, but what they do is automatically, if you've configured these, the sharding code will send queries to execute on the query shards while it sends update, insert, delete, etc. operations to the data shards to execute directly there. So one big advantage of that is you can run intensive data load, data ingestion workloads concurrently with analytic query workloads with minimum interference between the two. So your ingestion workload is routed to the data shards while your analytic workload is routed to the query shards, so they are not contending for cache. Your queries have their own sets of caches across all of the query shards. Your ingestion has its own set of cache across the data shards. The second big advantage is you can have multiple query shards per data shard so that it gives you wider bandwidth for concurrent sharded queries. It doesn't make any one sharded query execute faster, but it means that you can have more sharded queries on behalf of more user applications executing at the same time without interference, just as application servers let your application itself execute with less contention from other applications that are executing concurrently. Now, joining tables is the big challenge for any distributed architecture because you've got to potentially do a cross product of rows from one table and rows from another that are residing in different places, and you need to come up with a way of doing that, minimizing data motion. This is where you can really get into bogging down your network. Now, our approach to sharding, thanks to leveraging ECP, you can perform any join reasonably efficiently, but we provide an approach that's really fast for those joins that you've used most frequently and that you've planned your schema to be most efficient. In the same way that if you know you've got certain access paths you use the most, you're going to build indexes on those. Well, if you know you've got certain joins you perform a lot, you can define what we call a user-defined shard key on each of those tables on an equivalent set of one or more fields. So if your join says those fields of one table equal those fields of the other table, the sharding logic knows that it must be the case that any pair of rows that's going to be joined resides on the same shard. Therefore, it can execute the entire join locally on each shard without having to do any cross-shard extra data movement. So it scales just as linearly as queries that don't involve joins. Now, the slight lack of flexibility here is that you get to choose one such join path for any given pair of tables. So for other joins you want to perform, we have another approach that will support any join, which uses what we call a shard tuple algorithm, where a shard tuple is a particular permutation of this shard of this table, this shard of this table, so on for all those sharded tables that are being joined together. And this algorithm assigns each of those to be executed on a given shard in a way that will maximize locality of reference while minimizing cache thrashing, so that as each shard goes through its set of shard tuples, it does it in an order that maximizes the chance that cache pages it needs will already have been used. This works still very efficiently for relatively low numbers of tables being joined or relatively low numbers of shards. The more shards and the more tables, the more it doesn't scale quite as well because there's a geometric combinatorial increase in the number of shard tuples. And we have enhancements in future releases to optimize some of those cases better, but still we're already seeing at least decent performance for virtually all sharded joins that any other product could claim to handle. Oh, and last point on that slide, as I'd already mentioned, you can join any non-sharded table to any sharded table transparently and very efficiently by leveraging ECP mapping. And all the mappings, by the way, and all the ECP connections used in sharding are all set up transparently. If you've used ECP and you're familiar with the configuration steps you have to go through with it, you don't have to do any of that just to use sharding, other than if you set up app servers, well, you would configure those as you usually do. But other than that, for sharding, it's all transparent and automatic. Sharding leverages some other features of the Iris data platform. In particular, it uses mirroring to provide a high availability. So all of the data storing components, that is the data shards and the master data server, can be mirrored. And when they are mirrored, sharding will automatically retry a query if one or more shards fail over during execution of the query. we leverage the topology that's set up when you configure shards for the InterSystems Iris Spark connector, which I think there will be some other presentations to talk about in detail, so I won't go into that here except to say that's a very powerful set of analytic capabilities that can leverage your sharded data or just directly make use of the sharded cluster. And finally, JDBC has transparently built into it the ability to detect that you're loading data into a sharded table, and behind the scenes will make direct JDBC connections to each of the shards so that it bypasses the shard master and loads each of the shards in parallels for very high speed, high volume data loads. I'm going to now turn it over to Harry to talk about use cases.
Thank you, Jeff. Yeah, so I'm here to share with you some real-time, real-world, of course, they're also real-time, as you can see, use cases. So these are our early adopters who evaluated InterSystems Iris data platform in these very demanding environments. So the first example I want to tell you is about this multi-asset trading system. So in the keynote speakers, even in the session prior to this one, Joe's session, all mentioned there's a investment bank is doing like billions of equity trades, but they are not just equity trades. Actually, they are actually doing all their trades globally on top of platform. So that's very demanding environment. So I will show you how they basically use Iris use Iris to tap into the existing cache-based trading system, as well as how to use InterSystems Iris data platform to replace or consolidate their other data management platform running on all other type of databases, such as Sybase ASE and Sybase IQ and Rainstor. So the second use case I'm going to talk about is another leading investment bank. They have this internal benchmark database, which is very mission critical. So their portfolio asset managers and as well as their trading desks need to access this benchmark data in real time. So they also want to consolidate their current Sybase and IQ-based environment. So they evaluated our InterSystems Iris data platform. They saw like amazing numbers. So I'm going to share that with both use case with you. So the first one is about this trading system. So this is, as you can see, this is actually what they have up to like early this year. So it's a pure cache ECP-based architecture. So as you can see, all those blue cylinders, they are the ECP data server. Then on top of this light blue cylinders, they basically ECP app server. They actually just called AS. So they run their applications, they call TSS on top of it. Then also they have their other applications called TIS, which will directly inject data, the insert update of these trades into these data servers. So they've been running this for quite some time, actually proven quite successful. But as Jeff already mentioned, that they actually have situation, they have to size their servers very precisely, because if you don't put enough data server or app server there, and potentially you have basically the performance will suffer, and then or you have to over-invest. But I just want, before I move to the next slide, I want to mention that even when they migrate to cache, they already solved their problem partially. Because before they built everything on one box. But with cache ECP, they can already do these horizontal user scale, as Jeff mentioned early on. So they can already use ECP to scale. So even the volume spikes, this whole system will guarantee will not fail. In the previous single node configuration, the system actually failed when it ran out of memory and disk, among other things. But now, since they pushed the envelope and now they are the entire trading system is running on this platform. So they ask InterSystems how InterSystems can help them to achieve like the real-time analytic and to scale the data horizontally. And also, more importantly, to cut down the cost, because in order for even to maintain the current system, they have to run on physical boxes. And besides cache as their intraday store, they also have this Sybase ASE and the Sybase IQ and also Rainstor for all different size and the different latency of data. And they give us the challenge, say, hey, can you help us to consolidate the whole data management platform and to reduce the cost, increase efficiency? So that's basically the challenge they give it to us. So what we are able to do to help this particular customer to achieve is that by introducing the InterSystems Iris data platform, and we can directly point to their existing infrastructure. So basically, if you look at here, these DSs are still their previous cache instances. But we are able to basically, so the DM, you already know, it's Jeff mentioned, it's our data master. It's actually our shard master. Then we basically point these query shards directly to their data servers. So these are their cache data servers. They don't even this is not Iris. This is Iris, InterSystems Iris, this is InterSystems Iris, but this is their existing cache instance. So for the folks here, you already deployed so successfully on cache, even on cache ECP. This is something you ought to look into, because what they found is that as soon as they do this, what happened? There's a couple of things amazing happen. One is that they immediately see this performance, the query performance hitting this DM. It increased the performance like by X number of times. X is basically how many these query shards or the data servers are. So here, in this case, it's 3X right there. And the other thing they found is that the cost, because in my previous slides, I show you the how big each of their app servers were. They were using our traditional InterSystems ECP architecture. So they, in order to avoid cache miss, they actually allocate like 3 times amount of the memory on each of these, if they were app servers, 3 times the amount of memory, and sometimes also more CPUs to handle the load. So with the query shard, they don't have to anymore. So the query, right now, actually the query shard has exactly the same amount of 40 gigabytes of RAM instead of 128 in my previous slides. So right now, actually, in those enterprise machines, the memory actually costs much more than our own like iPhone or laptops. But so it reduced their cost, and also more importantly, now they don't have to deploy at least these Iris nodes on the physical machine anymore. They still have, they already invest on these hardware, so they continue to run them as they were. But all these Iris, InterSystems Iris nodes, they're all deployed on virtual machines. Okay, so this is something that they found immediately. So this is the increase the performance by 300% and reduce the cost by 70%. So that's the challenge they want us to solve, how to improve their existing cache-based trading system. But the next one, they saw, this one has the potential. They say, hey, can you help us to consolidate our entire data stack? In my second slide, I described they have cache, they have Sybase ASE, Sybase IQ, and the Rainstor. So this is what's happening they're in the process to build up this infrastructure. Then this is a pure InterSystems Iris-based architecture. So on the right-hand side, this is every node is a InterSystems Iris node. So this DM is truly our shard master. This is our query shard. This is our basic shard, data shards. And so they also have this InterSystems Iris running in there. They're going to put in the production. So what we'll do is that we simplify their data platform, because simplicity actually is key, because it gives you the efficiency And also it gives you reduce the latency, and also it reduce your cost. So they are in the process basically let our InterSystem native replication. So we use asynchronous mirroring, and among those shards we do mirroring, synchronous mirroring, but between these two clusters we do asynchronous mirroring. So we can basically in the near real time bring their transactional data to this larger. So this actually will not contain 3. So since I don't have much real estate on this slide, but this one actually will contain, in each of their data center will at least contain 10 nodes. And then they have, for the analytical workload, InterSystem Iris cluster, where they are going to deploy in their 4 global regions, in North Americas, in the United Kingdom, then in the Europe, Middle East, and Africa, and as well as the Asia Pacific region. And so each of region they will have they will have 11 primary InterSystem Iris nodes, and then plus 11 backup InterSystem Iris nodes. So it will be also a it's actually, if you think about what they have right now, all the ASEs and IQs, they have hundreds of these instances. So by just using these like 10, or even we double it, 11, double it to 22, because we add all the mirrored InterSystem Iris node to it, it's still far more cost effective. And it's actually very scalable. As Jeff just mentioned, they can at the runtime dynamically add one or more of these query shards. Then if their query load goes away, their user disconnect, they can dynamically shut down these shards, and they're on the container, on VMs. They can just spin down the container or shut down the VM and reallocate the VM for other purposes. So that's how flexible we give it to them. We give them to a very cost-effective infrastructure. For this is their transaction process, and this is their analytical process, and very scalable. This will scale to the thousands of concurrent connections. So that's for the first use case. And my second use case is with this large investment bank. As I described that to you, they have this benchmark database with 18,000 of benchmarks with all the history. So it's total is 8 terabytes of data. And currently they are running on those big boxes of Sybase ASE and Sybase IQ. And by deploying similar architecture I showed you in the previous slides in the InterSystem Iris cluster, first everything is on virtual machines, and each of these virtual machines has only 8 core, 96 gig RAM, 300 gig local disks. And they were able to process these benchmark queries, because imagine they're either users using various trading apps, or their trading desks use those automatic program trading algorithm. They generate the request to this benchmark queries. InterSystem Iris was able to basically deliver the response time in it's actually a fairly complex query. Although under NDA I cannot show you how the query looks like, but I can describe to you. It selects hundreds of fields. It joins up to 5 different tables, because that data schema is highly normalized. So it's doing a lot of join and outer joins. And the InterSystem Iris cluster is able to deliver the response time for the smaller result set in the tens of milliseconds. Then even for the largest result set, it's only in the 50 milliseconds. Their existing product, the data management product, need to take hundreds of milliseconds. Some of them would take seconds to handle these kind of queries, especially under high concurrency. So that's another thing, is that if you not only have complex queries, think about this sharded and also ECP-enabled InterSystem Iris data platform. And in some cases, hey, if you have a lot of concurrent users, and especially these user loads are not predictable. You don't know when they are going to log on at the same time hitting your the data platform. And this is for that use case. So under these stress, and the InterSystems Iris data platform will consistently, because all the benefit as Jeff described in his previous presentation, how scalable adding those query shards, data shards, and even the AMs on top of these DMs. So we basically give you multiple level of the horizontal scalability. So that's where we can consistently deliver these very fast, actually it's 10 times or sometimes 20 times faster performance than the other competitors. I think that's, yes, okay. So I talk about the complex join and also low latency requirement. So we are 10 to 20 times faster than the, yes. So up to 10 to 20 times faster than the IQ, then at least, so also I want to mention, so there's other competitors doing sharding alone, so in-memory sharding. So you think, oh, they are all sharding are the same, not the same. So we are at least twice as faster as other in-memory sharding. That actually, I would say, thanks to Jeff and his team for utilizing our ECP. So we are more efficient if you don't have to put everything on one shard, we can efficiently bring the result back. On the other purely sharded environment, they had no choice. They had to either replicate the data or store a replica copy of those non-sharded table on local disk. That's where we beat them like by 2x. So I think that's the end of my presentation. And Jeff, please.
So I encourage you to come tomorrow at 5 p.m. I'll be giving a flash talk in the tech zone on next steps in sharding. We've been talking about what's available in the first release of Iris Data Platform, and this will explore what we're looking at for the roadmap beyond first release. John Payne is also presenting a related session. We want more solving scalability, which looks at some of these same issues at a little bit higher application vantage point. And, well, you see some pointers here to where you can get more information. And we have 2.5 minutes for questions. Are there any questions? Yes?
How do you define the breakup of data into shards, or how does it suss that out?
I'm sorry, how do you define?
Do you have a table that you say you want that table to be sharded, how does it know where the data ends up in the shards?
So there are two approaches. If you've defined a user-defined shard key, then it sets up a shard map and does a hash on the shard key values to figure out where each row goes. But if you don't define the user-defined shard key, then it sends the rows at random to a shard, but the algorithm for assigning system-assigned IDs takes the shards into account. It allocates ranges of IDs to each shard in a way that is a multiple of the block sizes used for bitmap indices, so that your indexes are just as efficient on each shard as they would be in a non-sharded table.
Yeah, and also I want to add that the way that you configure InterSystems Iris is extremely intuitive. It's like if you're familiar with our ECP, you know how you have to set up like a ECP server, data servers, app servers, then you do global mapping, package mapping, among all the many things you have to do manually, although many of my customers do that programmatically calling our APIs. But thanks to Jeff's team, all of these are all done by like just one API, say enable sharding. There's a $system.big data and enable sharding.
Right, you make that one call, and then when you define a table, you just put the keyword shard in the table definition, or optionally shard key, and specify the key just the way it might say primary key or foreign key. That's all you have to do. The rest of it's transparent.
Very minimal coaching.
Yes.
Can you mix and match hardware and operating systems?
Sure. We actually do that a lot when we're kind of scrounging machines for testing, you know, whatever's available. Yeah. Yes.
What sort of infrastructure do you have, or management infrastructure, for optimizing the QSs versus the DSs in that architecture that you have there? So if you're trying to decide how many QSs you need versus how many DSs and how to optimize that, do you have a
For
management
first
framework
release,
for that?
that's pretty much manual planning, and we have, as far as how you configure all this, there's a manual config API where you can install instances on machines in the conventional way and then assign them their roles, but also really the recommended way of deploying, particularly on the cloud or on virtual machines, is to use our new cloud-based ICM, InterSystems Cloud Management software, which will do all this automatically. You can just script it, it'll set up your whole shard cluster for you. But as far as the decision, you know, how many of it each you want, we have documentation that recommends rules of thumb for deciding these things, but we're looking at more sophisticated centralized management tools in next release.
Is a Shard master typically a larger machine?
It doesn't need to be. In fact, if anything, it might not need to be as large, because the heavy lifting of your queries is going to be happening on the Shard servers. The Shard master is just doing the relatively simple work of the final combining and aggregation. Although since in the current implementation, that happens in cache temp on the master, so you want to have a big enough cache temp database and enough I/O capability to handle that, but the heavy lifting is on the shards.
And also, since we also allowed you to add those application master server or AM to the shard master, so you don't have to basically, so literally you can use everything. You use the cookie cutter from Amazon, just the same VM, and you assign different roles. That's how you gain the horizontal scalability.
Well, thank you very much, everybody.